We're going to talk about conventional systems, first of all. The basics of conventional. We're going to talk about repeater operation. We're going to talk about signal boosters and distributed antenna systems. We're going to talk about receiver voting and simulcast and multicast. Now, some of this may be pretty basic for some people. I suspect for some others it may not be. So it'll give us all the basics before we move along. So what do we mean by conventional? We use this term in the industry a lot. It's a conventional radio system. Well, today it basically means it's not trunking. So the whole land mobile radio world is divided into and not trunking. And the not trunking side is simply called conventional. Simplex is a term that's used a lot in conventional. That basically means one-way communications at a time. A conventional system can be either analog or digital. That's true with trunking also, although most trunking systems today are going to be digital. With a simplex system, the users share a common frequency, and that means they have to compete for airtime. Only one person can occupy a channel at a time, which means the users have to monitor the system before they start a call to hear if it's busy. There are some remediations to that, squelch code or digital encoding. These are ways to provide some privacy but not security. There is possibility of congestion on the, so access time may be an issue. So let's use some basic terminology so we know what we're talking about. Here's 4 terms that you're probably familiar with, but if you're not, we'll review them. First of all, single frequency simplex. That means 2 radios that share one frequency, so you can only transmit or receive at a single time. You can't listen and talk simultaneously. Then we have a variation on that called 2 frequency simplex, where you have one frequency for one direction and a different frequency for the other direction. This is nice, but you can still only transmit or receive, but not both simultaneously. There's a couple examples we'll talk about where this is used. It's not very common. Then we have duplex. That's where you have 2 separate frequencies, one in each direction, but the difference is you can simultaneously transmit and receive. And the most familiar example of this, of course, is cellular phones, which use duplex frequencies so that you can talk and listen at the same time. So the primary difference between land mobile radio and cellular technology is simplex versus duplex, the ability to talk and listen at the same time. But we have a hybrid in there called half duplex. The mobiles and portables that we use in land mobile radio generally operate in simplex mode. They can be on one frequency or 2 frequency, but they still can't talk and listen at the same time. But we're going to talk in a minute about repeater operation. Well, a repeater does operate in duplex mode because everything it receives, it automatically retransmits. So it operates in duplex. So when we have a link that involves a repeater, it's called a half duplex link because half the equipment is operating simplex, the other half is operating duplex. So the entire link is referred to as a half duplex link. So let's talk about some basic conventional systems that are out there. Here we have vehicles that are talking in conventional simplex. They're single frequency. They can only talk unit to unit. They can only talk as far as the signal can transmit to the horizon. So they have a limited range. There's really no inherent security yet. So it's a line operation, and it's simplex. You can only talk or listen at one time. You may have heard the term PL or DPL, or you may have heard the generic term CTCSS. This is a way of providing some level of privacy when we're sharing a channel. If we have several users sharing a channel, but we only want to talk to selected users in our group, then we can provide a tone-coded squelch system where we embed a signal into our voice signal, either a tone or a repeating digital signal. We are receiving units with the ability to decode only those signals that have that tone-coded squelch on it. Therefore, even though many people may be talking on the channel at the same time, only the ones with our selected tone-coded squelch can be heard by it. So we're not providing security. The channel still has many people on it, but we can only hear those within our own group. There's another variation called two-frequency simplex. Here we have one channel for outbound and one frequency for inbound. And we can do that in a dispatch operation like taxis or buses, where the units can talk to the dispatcher on one frequency and they talk back on another frequency. This is not a repeater, but it's one-sided audio. So the taxis in this instance will only hear the dispatcher and not the other taxis. And that's the way they want it to be. And it works for them. Now, here's the most common thing we have out there in conventional, and that's called two-frequency half-duplex, also RT repeater, which stands for repeater talkback. A repeater is the most common way we have of extending range in a conventional system. So what we do is we take a base station, give it the ability to operate full duplex and automatically retransmit anything it hears, give it a different transmit and receive frequency so that the frequencies don't interfere with each other. And now when the unit talks to the repeater, it goes in on one frequency and the repeater transmits on a different frequency simultaneously. And most of you have heard of these. There's two different types shown on the picture. The one on the left uses a separate antenna for transmit and receive, and the one on the right uses a single antenna with a duplexer. And in Module 5, we're going to talk more about duplexers and how they work. So any audio received on R2 is retransmitted on T1. So this will give us good mobile-to-mobile communication because we can put the repeaters in a good location with good antennas and high power and get a lot more coverage than we would if we were trying to talk direct unit to unit. So here's how it works. We're going in on the blue channel or the blue frequency, and we're going out on the red frequency. We can cover much more range. Why? Because we have higher transmitter power. Typically a mobile will put out 30 watts, a portable maybe 5 watts, but a base station typically would put out 100 watts. So we have the advantage of more power. On the receive side, we typically have a better receiver sensitivity on the repeater's receiver. We'll have a better antenna height because we can use a fixed tower location or a building top where we can get more height. We can use higher gain antennas than we ever could in a mobile and portable environment. And so therefore we can get through the repeater and get a lot more range. Sometimes we have to share a repeater with several user groups. And a repeater that serves several groups of users is commonly called a community repeater. And it's a type of repeater that employs several of these PL codes that pass through it. And all the units within a group, well, all the units that belong to that repeater transmit on the same frequency pair. and they'll go out on the same frequency. However, you will only receive the signals from the units that have the same squelch code that you have programmed in your radio. So that means you can support multiple users and you'll only hear your own group. And as we said before, the disadvantage is they're still out there. The other people are still out there. So in order to use this type of system, you have to disable the squelch code on your receiver so that you can hear if there's any activity before you talk. And if there is no activity, then you can go ahead and talk. So it can be a little bit of a nuisance. They call that the monitor function when you just your receive PL prior to transmitting. So just like anything, listen before you talk. There's another type of special kind of repeater called an RA repeater, which stands for remote access repeater. This is where you have two repeaters back to back, where the receiver of one feeds the transmitter of the other. And the reason you do this is to extend the range far beyond where it would normally go. So for instance, if you had a mountaintop you wanted to get on the other side of, you could put this setup on the mountain. It would receive the signals from one side, cross over, and retransmit them on a different frequency on the other side. The disadvantage, of course, is you need 4 frequencies to do this, which is not always easy to get in a Part 90 conventional system. And you have to your link propagation, delay, and distance. Also, if you're doing any digital work or encryption, then you have to think about delay from decoding, encoding, and re-encoding. But it does provide an extended coverage area. Next, we have a vehicular repeater. You may have seen these. They're primarily used with responders, police, and fire, where in the mobile radio, it's a special type of mobile radio that's actually 2 radios in one. One of the radios is a standard mobile radio that talks to the system repeater, whether that's a conventional repeater or a trunk system. So half of the radio is a standard mobile radio on the system frequencies. The other radio is programmed with additional frequencies for local operation. So for instance, if you were a police department and you had an operation that was very localized, you wouldn't want to tie up the system frequencies with it. So you can have a set of frequencies you use in local operation. The mobile operator on site could, at his discretion, allow you to either operate locally or allow you to talk to the system repeater and the dispatcher as you need it. So it will repeat locally for good operation locally, and if needed, it can then extend coverage to the system. So that's why it's called a vehicular repeater. It repeats locally, but it also has a system link. So let's talk about the difference between analog and digital in the conventional world. So again, we said a conventional system was not trunking, but it could be either analog or digital. If it's analog, it will employ AM or FM or some other type of analog modulation, which affects the analog characteristics of the audio. A digital system is one that will convert audio into the ones and zeros through some of the digital modulation techniques we'll be talking about later. If it's digital conventional, there's different standards we're going to talk about. These include P25 and DMR, or some other digital. In the digital world, we don't use the PL tones. We'll use what they call network access code, which is the digital equivalent. So only users with the correct network access codes can be recovered by your receiver. So to sum that up, all the local radio systems out there will fall into one of the 4 groups: either analog conventional, analog trunking, digital conventional or digital trunking. Okay. Next, we're going to talk about signal boosters and distributed antenna systems. You probably run across these quite a bit. They're getting very popular, and in fact, they're mandatory operation in some areas. So we're going to talk about what is it and why would you need it. Well, the reason signal boosters are out there is because we have these two-way radio systems and they work great outside in a vehicle, out in the open. But when you get in some heavy buildings, and I'm talking about factories, shopping malls, hospitals, industrial buildings, commercial buildings, government buildings, they have a lot of walls. They can sometimes be thick walls that you just can't get the signal inside. So you have to have a way to get the signal in the building, distribute it all around the building, and provide two-way communications back to the system. So that's where your signal boosters come in. There, by way of terminology, there's two terms that generally get used. One is called a BDA, which is bidirectional amplifier. That's also called a signal booster, which is the FCC preferred term, signal booster. We like to call them bidirectional amplifiers because that's what they are. They're amplifiers that go in both directions. You'll also hear the term DAS, which stands for Distributed Antenna System. So DAS refers to the antenna system in the building, where BDA or signal booster refers to the hardware that boosts the signal in both directions. So let's see. What's in one of these signal booster systems? Well, the way they work is they basically take a signal off the air from a system that may be some distance away. And because of this distance, the signal is too weak to penetrate the building. So it will take this signal through a directional antenna, typically like a Yagi type antenna, pointed towards the closest system or repeater site. Bring that signal into the building, send it into the signal booster amplifier, and then it will distribute it through the building. It may be initially through fiber optics or it may be through coaxial cable. Eventually it will turn into coaxial cable and feed antennas within the building. There may be several antennas or there may be several hundred of these antennas in the building, depending on the building. And the engineers have software that will design these systems to allow full coverage throughout the building and determine how many antennas are needed and where they need to be located. So we've got the donor antenna, we've got the signal booster or BDA, and we have the internal distribution system. And that internal distribution system is called the DAS, the Distributed Antenna System. So eventually you will work with a portable radio inside the building and get as good or better coverage than if you were outside. So the FCC has classified these BDAs into two different categories. First one is called a Class A BDA. These are channelized and more narrowband, so they operate only on one or more specific channels. And they do have to be licensed and have to be operated by the primary licensee. A non-licensee has to get permission of the licensee to use these. The FCC defines these as a BDA that has less than a 75 kilohertz passband. So that's about 3 of the old analog 25 kilohertz channels, or about 6 of the 12.5 kilohertz channels if they were all adjacent. The second type is called a Class B BDA, and this is a wideband BDA, transmits over a wider frequency range. It has to be registered FCC, and it is defined as a BDA having greater than the 75 kilohertz passband. So this is when you need to operate an entire band of frequencies within a building. They can only be operated in fixed locations and not mobile. And in each case, your BDA power is limited to 5 watts of effective radiated power. So here's the diagram that shows what goes on inside the building with a distributed antenna system. So again, the signal comes in from the donor antenna, goes into the booster or BDA amplifier, is distributed either by cable or fiber throughout the building, and is then distributed through splitters on each floor, throughout in each room in the building, to antennas throughout the building. So we have the major components being the coax cable, the various connectors, splitters, and couplers, internal antennas, and any surge protection devices needed. So when we're designing these distributed antenna systems, we have to find what buildings we want to put them in and which don't require them. We can't afford to put them in every building in town, but we have to prioritize which buildings really need them. So we have to identify which ones may be a problem. Well, the rule of thumb that's come along in the industry over the years is that if we have about 16 dB loss going through the walls of the building or greater, it's potentially a candidate for a distributed antenna system. And that can be measured by signal measurement equipment. Look at the signal level outside the building, go inside the building, take it again, and measure the difference. If there's a big difference, then we're looking at a candidate for a bidirectional amplifier. Because at that point, you may not be able to have reliable coverage in all parts of the building. But again, that's a rule of thumb. It really depends on the individual building, and actual measurements always should be taken. Any questions up till now? Okay. We're going to talk about receiver voting systems. So way back in the dark ages, there were only mobile radios out there and base stations. And both the base stations and the mobiles transmitted at about 100 watts. Maybe they were less, maybe 60 watts, but they were both fairly high powered for what they did. Because they were using the same amount of power, in general, the talk out area was roughly equivalent to the talk back area. So if you could talk 5 miles, you could talk 5 miles in both directions. If you could talk 10 miles, it worked in both directions. And that was okay.
Hey, Bruce.
Yeah.
Somebody did raise their hand and had a question. I don't know if you
Okay.
saw it or not. It was the question, I think, was from Nikki. Wanted to know if you could go back 2 slides. That's
Okay.
all the question was.
Okay. This slide or back some more?
Nikki, can you unmute and ask your question? Sure, if she's got her mic working or her unmute is working. I think she said go back 1 more slide. That we may. Can you not see her? Can you not see her text?
Let me bring up the. Let's see. Bring up the chat. Okay. There it is. From Nikki, can you go back 2 slides? The one listing Caspi. Okay, hold on. Okay. This one. Okay. So the question is, oh, okay. You just wanted to mark it for your records? Okay, no problem. Were there any other questions? Okay. By the way, the hard copy slides will be available after the presentation, which is not to say you shouldn't be listening because, um, it's all good information and that's the time to ask questions.
Bruce, this is a
Okay.
huge issue for us on the West Coast. For example, in Las Vegas, from that shooting, I'm told that the casinos are putting in a lot of these now, and we have a lot of interference issues in LA. So this particular topic of the BDAs is a pretty hot topic for us, and particularly with lowest cost bidder putting these in poorly, number one, and number two, them not understanding the rules that they must get permission of the licensee. Otherwise, essentially, they're a unlicensed transmitter for the narrowband stuff. It's a big deal.
Exactly. That's true. And I will add that in many cases in the public safety community, for instance, the county where I live, a new trunk system's going in, and one of the provisions of the contract was that uh, there will be uh, good coverage, measurable good coverage in a whole list of designated buildings. And the question then arises, okay, we know what the solution is. This is good technology that works. However, we'll pay for it in each building because there is obviously a cost associated with it. So in many cases, if it's a public building, a government building, the government will pay for it. If it's a private building, a factory, a shopping mall, some commercial building, then there are actually requirements in the law that require the building owner to pay for a BDA system. They're not real happy about that, but they would be less happy if their building burned down because the first responders couldn't talk inside the building. So it becomes a political issue more than a technical issue. The technology's there, but as you mentioned, there are a lot of problems with these things if they're not installed properly, and there are unlicensed transmitters out there that you have to be aware of that will send out spurious signals. So, portables. When portables came along, we no longer had equal talk in and talk out. So now we have portables that put out 2 to 5 watts, and they're not going to do as well. And so we have a discrepancy between our talk in and our talk out coverage areas. That was a problem. So what to do now? The solution that came out and is pretty popular today is a receiver voting system, whereby you take a series of remote receivers. These are sometimes called satellite receivers, but I don't like that name. People think it has to do with satellites, and it's not. They're remote receivers that you distribute around the service area that pick up the signal and send it to a central device. And here's the difference between our talk in and our talk out coverage. So if you could then receive from multiple points, you could then equalize your talk in and your talk out coverage. And that's basically what was happening. So how do we do that? We do it with a device called a voting comparator. And let me go back and So receiver voting is a way you can select the best signal from these distributed receivers. The comparator unit is the piece of hardware that does that. They are made for both analog and digital systems. So you'll have multiple receivers. You'll try to select one with the best audio quality, and there's different ways to do that depending on whether it's analog or digital. The process will be dynamic and continuous. Its effect is on the talk in or receive side. It has no effect on the talk out or transmit side. The voted audio that comes out, what do we do with it? We're going to route it to any of a number of places, typically the dispatch console, the transmitter of a repeater, or a logging recorder. And I see we're at 50 minutes now, and we're going to take our first break for today. And I'll check the chat screen for any questions that came in. But take 10 minutes break, and we will resume at the top of the hour. I'll resume where we left off. We were talking about receiver voting and the fact that we use a voting comparator to select the best audio, take that and route it to the dispatch consoles, the various repeaters, to a logging recorder. In the digital world, we will, let me see, back up a minute. Oh, I skipped the slide. Analog. So for analog voting, what we do is we have a connecting link between all the receivers and the comparator. And when there's no activity on these links, we send a status tone of 2175 hertz. And the purpose of that is to determine that the channel is still available and it's not dead. So when audio comes in on one of the receivers, that tone goes away and is replaced with the audio. And in the analog world, the comparator will then vote the signal or select the best audio by looking at both the signal strength of the signal and the signal to noise ratio. So there may be 3 or 4 signals coming in, but it will select the one that sounds the best in accordance with the signal to noise ratio. So in the digital world, we do it different. We don't have signal to noise ratios in digital, and signal strength is not a good indicator of signal quality. So we will base our decision on looking at packets within the digital signal and look at the bit error rate metrics. So bit error rate is a metric that is used to determine digital quality by looking at the percent of bits that are invalid or corrupted. So for if we have 100 bits coming in and 5 of them are incorrect, then we have a 5% bit error rate. So since packets are coming in constantly from all the receivers, we're looking at them continuously. We don't always continually vote one receiver. We'll select one packet at one instant and possibly another packet in another instant from another receiver. And so what we're able to do in this is take the best packets from each receiver, and they're all synchronized, and then reconstruct a new string of packets that could actually be better than the packets received from any single receiver. So you're constantly picking and choosing the best packets, building a new bit stream, which is better than any of the inputs themselves. And that's the inherent advantage of digital voting over analog. So that's on the receive side. On the transmit side, a way we can enhance coverage to cover a wide area, there's two different methods, simulcast and multicast. So we're going to start with talking about simulcast, because that's probably the most common. So what is simulcast? The normal definition would be the simultaneous transmission of a common audio signal from two or more transmitter sites operating on the same RF frequency. So send the same signal over multiple sites at the same time on the same frequency. What are the advantages? Well, it provides wide area coverage. It lets you all over the area and not have to worry about it, changing channels as they move around. It uses the frequencies efficiently. And by that I mean, since it uses the same set of frequencies everywhere, we don't have to select separate frequencies for every site. That's both an advantage and a disadvantage, as we'll see when we talk about multicast. But the reason that simulcast is the most prevalent type of wide area coverage is because frequencies are hard to get, and it's easier to license a simulcast system with a set of frequencies over a wide area than to get a separate set of channels for every single site in a wide area system. So it will provide improved coverage by doing that, but there is a lot of designing that has to go into it. So here's a sample of a 3-site wide area system where we have 5 channels, and we have an example where a car in one area is talking to a portable in another area on frequency 2. So the same signal is being carried at all 3 sites, but there's nobody at the 3rd site, so that's kind of a wasted resource right there. We're using as many sites there are, we're lighting up that channel at every site, even if there's only 2 people conversing. But again, it's done because it's a lot easier to get 5 channels for a wide area than 15 or more. Here's the roaming, and as the car moves along, he won't have to think about where he is or change any channels based on his location. And again, it's improved coverage because no matter where you are in the service area, overlap or non-overlap area, you will get covered. So we said earlier that simulcast was the simultaneous transmission of a common audio signal from 2 or more sites on the same frequency, but that would really only be useful if the coverage area falls directly between the sites. The reason is that you have delays in the signal, that if you're closer to one site than the other, then you'll get delay, even though the signals are transmitted simultaneously. Depending on your location, you may not receive them simultaneously. So a system is designed to provide constructive combination in the overlap zones in the non-capture areas. If you are close to one of the transmit sites, you're in the site's capture area and you'll be fine. If you're in a overlap area, you want to be able to receive the signal simultaneously in phase from multiple sites. So that's where the design comes in. So capture area is defined as the area in which you will be captured by a single site. If you're in the upper left site, you'll only be talking through that site because you're not strong enough to capture the receiver on the other 2 sites. And you're fine as long as you're there. But when you move into the overlap areas, now your signal is contending with several sites. So you have to worry the placement of sites and how you're going to take care of those overlap areas. And the designers have software tools to do all this, to help them figure out where to put the sites, where are the capture areas, where are the overlap areas, and what is the effective terrain. So to illustrate that, we have a little simple example here where we have two sites, side A on the left and side B on the right. We have a portable in the middle that wants to get coverage. He's about halfway in between those two sites. And that's good because if you look at the animation on this graphic, what's happening is site A and site B are transmitting at the same time. So the signal is received by that portable at the same time from both sites, which is good because then the signal will be in phase and everything's good. So if they're in phase, you'll get a recovered signal that's in phase. If they're even 90 degrees out of phase, you start to get a corrupt signal. And if they're 180 degrees out of phase, then the signals will cancel each other and you'll get complete cancellation. And that's the worst case. So it has to do with the spacing of the sites relative to the coverage area. So one thing we can do is figure out where the coverage areas need to be and design the system so it doesn't launch all the signals simultaneously, but actually puts intentional delay in some of the sites so that it's received simultaneously. So the key in simulcast is not to transmit simultaneously, but to receive simultaneously. So here's an example where I've moved my desired coverage area closer to site B. If we were to launch simultaneously, the signal from site B would get there before the signal from site A, and you'd get cancellation. So how do we overcome this? Well, if you look at this animation carefully, you'll see that site A launches first, and after a delay, then site B will launch. And the result of that will be that the signals will be received in phase in the desired coverage area. So how can we delay the signal? Well, with the equipment out there today and the software, you can set delay into each site so that it will optimize your phasing in the received coverage area. So what do we have to do to be successful in simulcast? Well, we have to provide the identical RF frequencies from the transmitters at each site. It needs to be very high stability type transmitters where we don't have a lot of frequency drift. We also have to control the amplitude because if one signal has a different amplitude than the other, then you'll get amplitude cancellation. And as we mentioned, you have to control the delay so signals arrive in phase at a subscriber's radio. So how far away are the sites? Well, that depends on the type of modulation we're using. In the analog FM world, it was much more tolerant of delay. So we could space our sites up to 22 miles apart from each other. But as we develop new and better digital technologies, it became less tolerant of delay because the bits got smaller and faster and were less tolerant of delay. So 9600 bit per second trunking with 12.5 kilohertz spacing, we were down to about 6 mile spacing. So again, this course is not about designing systems, but the people who do design them have to keep all that in mind. Those rule of thumb distances, rules of thumb. We can adjust the simulcast launch delay, can adjust the antenna patterns, and adjust the transmit output power to give us the coverage we want. And my last slide in this deck is to talk about simulcast versus multicast. So we talked about the fact that simulcast sends approximately the same outbound signal to all sites on the same channel. We talked about delay, but apart from that, we're basically sending the same signal on the same frequency from all the sites. Multicast, on the other hand, will send will send the same signal out, but we'll do it on different frequencies at each site. And by doing that, you can select only the sites that, that have users within your particular user group. So in the example on the left, we have 2 users that are talking to each other in a wide area 6-site simulcast system. Even though there's only 2 users, we have to transmit on all 6 sites on the same frequency at the same time. So that channel becomes unavailable to all the other users at that time. So even though it takes less frequencies to make it work and it's easy to license for it, it's not super efficient as far as user throughput. The multicast on the right, each site is represented by a different color dot, meaning it has a different group of frequencies, so that the same 6 channels, if they're involved in one-to-one communications between 2 users, could actually support 3 simultaneous conversations. And even more if the users were affiliated to the same site. It could theoretically support 6 simultaneous conversations at once. In this example, it supports 3, but you can see how simulcast is not as efficient as multicast in terms of the number of users that can be served, but multicast is hard to get, and all these different, if you were talking a 5-channel system, left would require 5 channels. The multicast system on the right would require 30 channels. So it's very hard to get a system license for 30 channels. And so that's why you don't see simulcast very often. The exception I've seen is in the US government and D systems on military bases. Multicast is fairly common because they're the only people around using those frequencies and they can get more of them. But in your typical Part 90 and trunk systems in the rest of the country, simulcast is more common.